All right, so today we're going to be taking limits analytically or with an algebraic approach. We did it last week by looking at graphs, by looking at tables. We're going to take those away today. I'm not going to revisit the graphs and tables right now because according to your Google Forms, you thought that went well. There's one person who didn't. That person should seek me out during a Google Meet. I don't want to redo it for everybody when most people said they had a 80% or better grasp of it. So let's hop right on here. We've got an absolute value graph of a function over here. And from the graph, determine the following limits. So first of all, it says just, we have x approaching a. So in this one, a is 0, a is 2, a is 10. And it says find f of a. So I am looking for f of 0, f of 2, f of 10. Okay. And so f of 0 is what I get when I put 0 in for x up here. And I would have 1/2 of 4, which is 2, minus 4, which is -2. Now, it shouldn't be a big surprise that as I graphically approach 2 from both directions, I arrive at -2 on f of x. They match. Cool. All right, so now let's plug a 2 in. All right, so when I plug a 2 into f, I would have a half of -4 plus 4, or a half of -4 plus 4, which is 0, or a half of 0 minus 4. I'd be at -4 when I do the arithmetic. And again, as I approach 2 from the right, here I am at -4. So I'm at the same place on the graph as what I got when I just plugged the number in. Well, now I'm approaching 10, and you'll notice right here, well, I can't get out to 10 on the graph. Uh-oh. Well, because this continues continuously like this, has no holes or asymptotes on it, when I approach 4 from the left, and I approach, 10, not 4, and I approach 10 from the right, I should end up at the exact same spot. So shouldn't I just be able to plug 10 in? And the answer is yes. Is it that easy? You just plug and chug on all these? No. But if the function's continuous, you do. So at the place where you're taking the limit. So as I approach 10, I would say, well, I will do a half of, and then I'd have -20 plus 4, -16 minus 4. So I would have a half of 16, which is 8, minus 4, which is 4. It means I know for sure that that graph is going to arrive up at 4 when I'm out at 10. Okay, so it appears that I can just plug a in to the function. And the answer is, yeah, easy peasy, you can, as long as the function's continuous at a. So watch, if a was right here, I can't plug and chug because I'm not continuous there. But if a was over here on this function, because I'm continuous over here, I will arrive at f of a from both sides. So you just have to know if the function has any basically big issues, and if so, is it at this point of approach. So parabola opening up doesn't have any holes or asymptotes. So I don't need to graph the parabola and creep in on 3. I will be at wherever f of 3 is. So let's just plug a 3 in, and we would have a half of 9 minus 6 plus 3. The constant stays the same. And then let's go common denominator. We would have 9 halves minus 12 halves plus 6 halves. So it looks like we have -3 plus 3 on the top there. Looks like I have a 3 halves. That is where this point will be located on that parabola. So does this rational function have any issues? Well, it certainly has an asymptote, because when the denominator equals 0 and does not cancel with the numerator, we get a vertical asymptote at 3 halves, but I'm approaching 3. So I'll be just fine at 3, right? So I will plug it in. On the top, I'll have 15 plus 2. On the bottom, I'll have 6 minus 3. Again, just plug, plug, easy peasy. As I approach 2 from the left, What happens when I plug it in? I'll get the square root of 4 minus 1 over 3. 2 minus 1 over 3. It's easy, right? Now be careful with the trig functions. However, we do know that the sine wave and all of its transformations is roly-poly and continuous everywhere. So it means you just need to, yes, know your unit circle. So I can just directly plug this in. As I approach pi halves, I will be at the exact same height as I am from the left as I am from the right, so I can just plug it into the function. This would be sine of 2 times pi halves, or just sine of pi. You need to know your unit circle without looking. Pi is over here. Sine is the y value. You should be able to do it that fast. Otherwise, you should practice. Now this function has an issue. It has an asymptote at 0. So had I been approaching 0, I'm like, I don't know. You don't know yet. That's coming. But for this one, I'm just going to go plug it in because I'm on a cosine wave, and I do have an issue at theta, but theta is not, at theta equals 0, I'm at 2 pi thirds, so I'm good. I can do cosine 2 pi thirds all over 2 pi thirds. So now I need to be 100% sure what is the cosine of 2 pi over 3. I need to get there. Either you immediately know, or you go 1 pi over 6, 2 pi over 6, 3 pi over 6, 4 pi over 6. You're over here. You want its x value. It's the same as the x value over here. Leroux said to remember that there's always a half in this far right. The other one's root 3 over 2. This one reverses. This is the same over and the same up. However, it's to the left. So cosine of 2 pi thirds would be negative 1/2 times the reciprocal of the denominator, 3 over 2 pi. And then it looks like we'll get a negative 3 over 4 pi. I don't like those slanted. Sorry, oops, I didn't grab the eraser. I still didn't grab the eraser. Come on. So we have 3 over 4 pi negative. All right, so logarithmic functions are continuous except at and to the left of their asymptotes, but they all kind of look like this. So at 9, I'm just fine with this one. So this would just be log of base 8, 11 minus 9, which is log base 8 of 2. Now, do you know what that is? That, that might require a little bit more work, but remember, a logarithm is an exponent. It's the exponent on the base that gives you the 2. So 8 to some power is a 2, and maybe you're like, oh yeah, the cubed root. But if you didn't know, you'd go like this. 8 to some power gives me 2. Sometimes people write like this and they remember base to the outside equals the inside, or however. You can, on this one, get a common base. So I could have 2 to the third to the x is equal to 2 to the first. Again, this is algebra 2. I get 3x equals 1, because when you multiply power to a power, you multiply those. So x is a third. So if you see, I'm fine if you see it. I'm fine if you need some work and you know how to do that work. The two things I'm not fine with are if you go do it on your calculator, or if you just go look at the key at that point. Make sure you can, again, I'm not going to give you any like this on the test yet. We are going to have some more with logs. So if you're a little funky with it, that's okay, but start working on it. So this is what happens if we try to evaluate the limits below by direct substitution. All right, so as I approach negative 3, I'm going to get, and I'm going to look here and see if the same thing happens. It's the first time I've looked at these notes. For all of these, if you directly plugged it in just to save yourself some time. On this first one, when I square negative 3, I get 9 minus 12 and then plus 3. On the bottom, I get 9 minus 6 and then minus 3. You'll notice both of those are going to 0. I get 0 over 0. That's a huge, huge issue. Okay, so for each one of these, if I did it over here, just trust me, when you plug in a 1 on this one, you're going to get, what do I get when I plug in a 1? I get 1 plus 4, I guess you don't just get it. I get 1 plus 4, 5, 6, 7, 8 over, and on the bottom I get a 0. That's a problem. In math, we cannot divide by 0. On this one over here, as I approach 1 from the right, I also get a 0 in the denominator. We cannot have a 0 in a denominator. It means one of two things, okay? And we'll discuss those two things up here, down here. So let's go see this one. Just because a function is undefined at a value of x does not mean that a conclusion can't be reached about the limit. Because remember, this, we could draw a conclusion that the limit as x approaches 3 from both sides is 4. And at an asymptote, we could draw the conclusion that the limit as x approaches 3 from the left is infinity. We could still draw some conclusions. So what it really means is more work is needed. So does not mean that you can't draw a conclusion. It just means direct substitution isn't working for you. So note to self, upon direct substitution, if you get it a 0 in the denominator, fail, okay? You have to do it a different way, and the different ways are coming up. So it says, consider the rational function above. From the graph of the function pictured to the right, what is the value of each limit? So again, back to a graphical approach. As I approach -3 from both directions, I'm on here with my red. I've got a limit at the y value of that dot, which is a half. Notice when I got the 0 over 0, it didn't mean the limit didn't exist. It didn't mean I was going to infinity. It actually meant that the limit was a half. How did that happen? We'll talk about it. As I approach 1 from the left-hand side, this function's going to negative infinity. From the right-hand side, it's going to positive infinity. Remember, from both sides, I'd write d and e. So look at what happens when I had this 0 in the denominator, but a constant on the top. Graphically, it meant I had an asymptote there, and I was going to one of the infinities. So what I know right here is when I get 0 over 0 upon just a second, I'm reading this question. The tag is just gonna see, I think this is my first time doing this since last year. I think that's gonna happen right here. The task now is to determine how to find these limits analytically. How was it that we found discontinuities of rational functions in pre-calculus? What does that mean? Discontinuities of rational functions in pre-calc. Remember what a rational function is, first of all. Let's put that down. It's a polynomial over a polynomial, like this guy here. A rational function, well, it's the same one on all of them. That's a rational function. How did you find the discontinuities? Well, you might have forgotten, so I'll tell you. What your pre-calc teacher did is they should have said you need to factor and cancel anything that cancels out. If you cancel okay, this implies that there's a hole in the graph. Watch. The hole here was located at -3, 1/2. Keep that in mind. Watch what happens when I factor this sucker. Okay. The minute I cancel, I know there was a hole. Okay, so canceling top to bottom is the location of a hole in the graph. So there is a hole at x equals -3. You might say, we already knew that from the graph. I'm saying, what if I didn't have the graph up there? How would I know if it's a hole or an asymptote? They both cancel for a hole in the graph. And the hole is at what you get when you plug this back in. So when I plug in a -3 to that, I'd get a -2 over, and when I plug it in on the bottom, I get -4. Notice how it gave me the y value of the function. It gave me the limit, the y value of the whole at which I arrived. So that's kind of cool, right? When you get 0 over 0, factor, cancel, replug. Based on our knowledge from pre-calculus, we know that if a rational function has a non-removable infinite discontinuity, aka a vertical asymptote. So graphically, a vertical asymptote, you can write that out, exists. Okay, so knowing that, just a second. I'm looking at something here. All right, since the y value does not approach one specific value from both sides at an asymptote, then the limit does not exist. What that means is the limit doesn't exist. We're going to one of the infinities. But we can, on a one-sided approach, determine whether it's negative or positive infinity, or if from both directions we can. Remember that graphically rewrite D and E when this happens. So one-sided infinite limits. What I'm saying is, if you come in at an asymptote from one side, you have to either go to infinity or negative infinity. So since this is a one-sided limit, and I knew I had an asymptote, I knew I had an asymptote there because I got 8 over 0. A number over 0 means you're getting an asymptote, and I saw it on the graph. So how do I, without looking at it, know whether I am heading to positive infinity or negative infinity? What you do is you do what I call be a creeper. So we're going to creep in. You pick a number directly to the left of 1, like 0.9. Okay. Now keep in mind we had factored this thing, so it ended up being, what was it, x plus 1 over x minus 1. It's easiest to look at the everywhere except there was a hole in the graph at x equals -3, but the rest of the graph was this function. So when I put in a 0.9, when I go directly to the left of 1, I end up with a positive number on the top. It doesn't matter what that number is, and 0.9 minus 1 is negative. What that means is I'm heading to negative infinity. So to decide which infinity you go to, you become what I call a numeric creeper. So notice being a numeric creeper matched the behavior of this graph as I approached -1 from the left. I was going down. Okay, so we say negative infinity. So to repeat this process, I plugged it in. I got a 0 in the denominator. I factored, I canceled, and I got that I was really taking the limit as x approaches 1 from the right of x plus 1 over x minus 1 after I factored and canceled. I knew there was an asymptote because, again, I had that number over 0. Now what I do is I come in from the right of 1 in my brain. Don't pick 10. You want to be really close to that asymptote and see what's happening. And you could pick 10, but we're going to think 1.1, 1.01. Just stay real close. On the top, I'll have a positive. On the bottom, when I go to the right of 1, I'll also have a positive. So because I know I'm at an asymptote, I have to go either up or down. My numerical analysis tells me I'm going to positive infinity. All right. So that was one method of dealing with what happens when you get 0 over 0 or a 0 in a denominator. First of all, you decide whether you have a hole in the graph or an asymptote by factoring, canceling, replugging. But what if you do a direct substitution? So this would be the square root of 4 minus 2. The top is going to 0, the bottom is going to 0. I'm at a standstill. Without looking at the graph, I have no clue what's happening. When I look at the graph, I'm like, oh, it's up there, not very far. But I still don't really know what it is because it didn't tell me what the point is. So the graph tells me there's a hole, which I know because LaRude said, and that's really important to take out of here. That might be a little great Schoology quiz question, is that when we get 0 over 0, that implies that you will have a hole in the graph. When you get a number over 0, that implies that you've hit an asymptote. It means your answer is either infinity, negative infinity, or if you're coming in from both directions and there's a split, we put D and E. So what am I going to do here? I'm stuck and I can't factor. So what we often do is we do rationalization, which is get rid of that root because I don't like it. By the way, because I put a 3 in and I got a 0 on the bottom, I also know there has to be an x minus 3 on the top. That's the only thing that 3 makes 0. You might say, how is there an x minus 3 on the top? Well, if we get rid of that root, I think we'll find it. So we multiply by the conjugate of the level that has the root in it, not the conjugate of the denominator or the numerator. It's wherever the root is. In this case, it's in the numerator. So I'm going to multiply the top and the bottom by the conjugate. Remember, the conjugate just changes the sign of the link, the plus to a minus or the minus to a plus. And we do it over itself. What I just wrote in purple will not change the value of the function anywhere because I'm really just multiplying by something over itself, or 1, but it gives it a facelift and it gets rid of the root or rationalizes it. So now what I'll do is I'll take that limit, as I know there's a hole there. I want to find the location of the hole because that is where I am. Even though f of 3 doesn't exist, its limit does in this case. So we're going to do firsts upon our FOIL. The roots will cancel, giving us an x plus 1. Outside and inside are opposites, so they'll cancel. And then our last are minus 4. Look it. Take a look at that top. I told you I knew there was an x minus 3 up there because when I plugged a 3 in, it gave me a 0. And if you plug a 3 into something and it gives you a 0, it has to have an x minus 3 in it. Look at this. Oh, I plugged a 3 in and it gave me 0. That's because there's an x minus 3 in it, right? On the bottom, I have the x minus 3 times the square root of x plus 1 plus 2. Now, these cancel. That's where the hole exists. There's a hole at 3 comma. Now, to do what we call remove that discontinuity, also known as plugging the hole, I want to figure out where it is. All I do is take that 3 and replug it in. I'd be careful that I know that there's now a 1 on the top, and that location of that hole is at 1 over the square root of 4, which is 2 plus 2, or a 4. So now I know this is at 3 comma 1/4, and I now know that my limit, my y value at which I have arrived from both directions is 1/4. Again, the limits of the function, the f of's are the y's. So I'm at 1/4. So now we have two methods for dealing with that, getting the 0 over 0. Factor, cancel, replug, or if you see a root, you're going to rationalize it by multiplying by the conjugate. All right, so I feel like there was another one on the bottom there. Nope. So now we're moving on. Right over here, we're not going to deal with piecewise right now. Okay, actually, we're not going to deal with that today. We're going to move on here with that page. So this says, consider the function below to find the limit. If a limit does not exist, state why. All right, so I'm going to put this over here. First of all, this is a piecewise function. You should be able to graph it, but you don't need to if you understand what has to happen graphically. But let's go take a look at what I have here. I have a function for sure that I know is undefined at -2 because there's no equal to there. So there is an issue at -2. It's one of two things. It's either a hole in the graph or it's an asymptote. Now, I know it's not an asymptote because -2 isn't causing a denominator to be equal to 0. So now I know there's a hole in the graph at -2, correct? But again, g of -2 doesn't exist, but there's a hole in the graph. What that means is where this parabola meets up with this line, there's a hole in the graph. Let's go look at it graphically. So first of all, that parabola actually at -2, let's go see where that would be. So at -2, I would have 2 times -2 squared, so 8 minus 6, which is 2. So at -2, 2, There's a hole in the graph. That parabola opens up, it goes through 0, 0, so I'm just going to go like this. That's what the graph looks like. Now after that, once I hit -2, I've got a line. It goes through 0, 1, and it goes down 1 over 2, down 1 over 2. It's going like this. So the purple is meeting up with the red parabola at an open dot, at a place where it's undefined. But as I come in from the left, right here, I was at 2. As I come in from the right, right here, I'm at 2. So therefore, because I was at the same spot from both directions, I'm at 2. So what that means is these two didn't need to be graphed. When you're given a piecewise function, to find the limit from the left, you just plug it in to the left. From the right, plug it in from the right. If they meet, that answers your limit. Now, if you had plugged it, if it was like different there, like had the parabola been like this, but then the line actually went like that, then from the left, we'd be at, let's say 2. From the right, my limit would be at 1. And then as I come in at -2 from both directions, we'd write D and E. So you can just plug that in. Find the limits of each analytically, show your analysis. So the first thing I do is I plug in. If I don't get a 0 in the denominator, I'm good to go. So this is just ln E over 2e. Ln E is 1. Done. Direct plug. Why? Because I didn't get a 0 in the denominator. So if there isn't a denominator, no worries, right? No worries, no worries. So on letter B, doesn't matter if you're doing a left-handed or right-handed or from either side. You're on a parabola. As you come in at 5 from the left and from the right, it's the same, and it's f of 5. So you just plug it in. I'm not going to do that. I will do this next one because it goes tricky. I'm going to see how much time I'm sitting at here. Okay, I'm good. All right, so we will do sine squared pi plus, make me hungry, 2 cosine pi. The sine of pi is the y there, which is 0. Square 0 and I get 0. Cosine pi is the x there, which is -1. So this is a nice -2. Next tricky one. I do have a denominator. I better make sure it's not 0. It's not. It's 5 pi thirds squared. So this one's just going to be tangent. And again, I'm just plugging it in because I'm not getting a 0 in the denominator. That's tangent 5 pi thirds over 5 pi thirds quantity squared. So now, unit circle. Remember those kids on the flip grid, they said you better know your unit circle. They were not messing with you. It's on almost every assignment. So tangent of, excuse me, 5 pi over 3, I need to get there. I sometimes like to turn it into sixths. I like to say that's 10 pi over 6, and I like to go backwards. So I'm going to go back 2 pi 6. It's down here. And then there was 11 pi sixths, right? So it goes with, erase it nice. Let's put a nicer unit circle on there. So it's this guy, 10 pi thirds, which goes up here with this guy, right? Which goes up here with this guy. These all have the same to the left and to the right distance. So we're going to go up here, and we're going to say Laroude said that the half is in the far right for this guy. So we're going to be the exact same over. So that's also at a half, but it's down, -√3 over 2. Perfect. But this said tangent. Tangent is sine, -√3 over 2, right? Over cosine, 1/2. All right? But when we divide by a half, we multiply by 2. So my tangent is equal to -√3. And then when I square down below there, I'll get 25. 25, my stylus is a little goofy here, 25 pi squared over 9. So I would, if I multiply by a reciprocal, I'd have -9√3 over 25 pi squared. That was fun, wasn't it? But notice the hardest part of that The unit circle. All right, so next one up, we always start by plugging that number in. I usually plug it in on the top and I'll get 4, minus a -2, which is +2, minus 6, top's going to 0. Now I plug it into the bottom. If the bottom also goes to 0, hole in the graph. So let's go take a look. It also goes to 0, hole in the graph. Now, if the top had gone to 6 and the bottom had gone to 0, asymptote on the graph. Okay, so we have a hole in the graph at -2 comma something. So what we do is we go factor to find that something. The top, we factor, and again, there's lots of algebra, so hopefully you know how to factor, right? That I am not teaching. 2 times x plus 2. There goes my issue. Okay, my issue at -2, I knew it would cancel because I knew there was a hole in the graph. I knew it had to live on the bottom and on the top somewhere. If -2 is causing a 0, x plus 2 is the only thing that can do that. I just found it on the top by factoring. So now all I need to do is replug this -2 in, and I'm at -5 halves. So the location of the hole is at -2, -5 halves, and I am there as I come in from at -2 from both directions. So this is the answer to the limit. All right, letter F. Again, plug it into the top going to 8, bottom's going to 0. What does that mean? Asymptotic behavior. How am I approaching 3? From the left and from the right. So what I do is I'm still going to factor. And I'm going to be a numerical creeper because I have to see what happens at that asymptote. The x minus 3 did not cancel. What that means is I have an asymptote at 3. I'm coming at it from both directions. So let's come at it from the left, which would be 2.99. We'll do sign analysis. On the top, I'll have a positive. It doesn't matter what it is. On the bottom, when I plug in a 2.99, I would have a negative times a positive, which is a negative. So what that tells me is from the left, negative infinity. But this didn't say from the left. It said from both sides. So I'm going to go try 3.01. The top is still positive. Now the bottom's positive, right? So when the top is positive and the bottom is positive, it means positive infinity. Now, because that was a two-sided limit, and we were going up in one direction and down in the other side, this is a true limit that does not exist. We don't always put D and E for this, though. Had they both turned out by being positive infinity when I was being a creeper, then we would have said that it's going to positive infinity, which by definition doesn't exist. All right, so next one up, letter G. All right, trying to circle it with yellow. I think I'm gonna wait on that because I'm not quite sure what I am for timing. I have to have a discussion about factoring difference of cubes usually at this time. So I'm gonna continue, and if I have time, I'll go back to that one. Otherwise, I might save it for another day. Letter H, College Board doesn't on the AP test have you factor sums and difference of cubes because they don't want you getting your calculus wrong because you can't do, sorry. This is like my third video today, I'm thirsty. Because you can't factor the difference of cubes. So, but you know, you should know how. But we'll move on to the next one. Again, we always, that's gonna be another Schoology quiz question. What do we always do when we're approaching a constant? You plug it in. Whether it's the left or the right, you plug it in. You hope you get a number because that's your answer. You hope 0 is in the denominator. If it's 0 over 0, we have a hole in the graph. If it's a number over 0, we have an asymptote. Very important from today that you know that. Now we said to rationalize this by dealing with the conjugate of the level, which in this case is the numerator, that has the denominator in it. Conjugates just change the link between the two terms to the opposite of what it was. So I'm going to multiply it by root 2x plus 5. Now think ahead. I know that somewhere in that numerator is an x plus 2. How do I know that? Because on direct substitution, when I plug this in, I got 0 on the top and 0 on the bottom. Well, I can see the x plus 2 on the bottom, but there is 1 on the top because negative 2 can't cause anything to be a 0 except x plus 2. So it's there. This rationalizing helps us find it. So we FOIL the top to rationalize or get rid of the root. Always keep writing that limit, by the way. You shouldn't drop your limits. This would be 2x plus 5. And then outside, inside always cancels with the conjugates. So then I just do lasts. Over, the bottom's the x plus 2 from right here. And this guy, it looks ugly, but it's just a lot of algebra, right? Now on the top, I actually have my limit as x is approaching negative 2 of 2x plus 4. Well, 2x plus 4 has an x plus 2 in it. I knew it had to. Again, because negative 2 caused the levels to be 0, both levels have an x plus 2 living in them. On the denominator, I have the x plus 2. And now in the rationalization of the numerator, I also have that large term as well. Cancel, cancel, that's where the hole was. Okay, now it was at negative 2 comma something. I need the something. The something is found by replugging that into your new expression. So let's go do that. On the top, 2 is always a 2 regardless, right? And on the bottom, I'd have the square root of 1 plus 1, which is, wait, what would I have? Just the square root of 1. Yeah, sorry, plus 1, which is 2. All right, so boom, boom. It means that when you go graph this on your graphing calculator, which I wish I had a graphing calculator out, from both directions that you approach 2, you will be up at negative 2, sorry, negative 2, you will be up at 1. But at 1, there's actually a hole in the graph, but you'll be there. All right, this last one, I'm not sure how far I wanted to get today. I think this is the last one I want to do. I would like you to do it. I'd like you to pause the video because this is what we'll do in class. I'll say, okay, guys, pause the video. I'm not pause the video because I'll be teaching it. I'll say, okay, guys, stop. Everyone go do it. And then I'll kind of have you, normally I'd have you check with each other because you usually have what's called a row partner, but we don't have that going on either. So I will walk around and check them. So I want you guys doing this from home to pause the video and go try this one on your own. All right. So here's the correct process. The first thing we always do is we plug our approach in and we just say, I sure hope I get a numerical answer that doesn't have a 0 in the denominator. Let's see what I get. I get 1 minus the square root of 1, 1 minus 1. The top is going to 0. Notice I'm not writing equals 0. There's a reason for that. That's coming later. It's going to, I don't want to write that this limit equals 0 over 0 because it doesn't equal 0 over 0. 0 over 0 is undefined. It equals something else. And College Board takes off for what we call linkage. So like if you were doing something like this, 1/3 of 6 plus 2, no, let's do 6 plus 3. 6 plus 3 is 9, 1/3 of 9 is 3. You wouldn't get this answer point because your train of thought caused you to say that 1/3 of 9 is 9. So this right here is not a true statement. And saying that this equals 0 over 0, it doesn't. It equals something else. So I use those arrows and you should start doing that as well. So now we go up 0 over 0. We have ourselves a hole in the graph for sure. I need to figure out where it is without graphing. So this isn't a factor cancel one, but it's the conjugate one. So in the trigger for that is when you see that red. So my limit as x approaches 1 from both directions, or from the right or from the left, it wouldn't have mattered. We have to multiply that top and bottom by the conjugate, and again, it's in the numerator, but it's because that's where the root is. So we do it times 1 plus root 2x squared minus 1 over 1 plus root 2x squared minus 1. All right, and you would have continued from there. We would have, this is going to be my last video today. I can tell I'm getting tired and it's not fair to you guys. So limit as x approaches 1 of 1 minus, don't forget to put this in parentheses. There's a huge So again, with our conjugation, the outside and the inside are going to cancel, and then I'm going to end up with a minus that whole chunk all over that whole denominator. All right, equals, and I should have been stressing this more, you really need to make sure this limit comes down with it as you rewrite it. I do take off on the test like just a blanket amount of points. If you drop your limits on the first page, I just go -2 dropped limits because it's not notationally correct. So it's kind of like your English teacher writing -2 for spelling. It's, yeah, I know what you're trying to say, but it's not correctly spelled. So on the top, I end up with a 2 from the 1 plus 1, and then minus 2x squared. So again, I'm just distributing this sucker in. On the bottom, I have the x minus 1 times, and I'm not going to write that whole thing out because I'm getting really ready to be done. This is my last one. It's got to be. I'm losing it. All right. Holding it together. So on the top, we're taking the limit. I just did 3 BC videos. So I'm just trying to kill them off here on Saturday because it's such a gross day. They're probably thinking I wear the same thing every day because in all of their videos for next week, I have on this purple sweatshirt. They're like, oh, she's gross. Anyway, I'm factoring the top. See what happens when I start to get tired? I go off on tangents. Pardon the pun. That was actually kind of funny. You'll figure out why later. All right, so on the top, I'm still factoring. Limit, x approach. You can see when I get tired too, my limits start to just sort of run together. I have a difference of squares on the top, a 1 minus x and a 1 plus x. And then on the bottom, an x minus 1. This is a lot of notes, I know. It's just notes today in class and for homework. And you only have to turn in a notes quiz. We're just getting them out of the way and then we'll go practice. So I did find my problem. Remember I told you that I know I have to have x minus 1 or 1 minus x on the top because that's the only way I can get the 0 over 0. But be careful because when these cancel, they're actually opposites. So they cancel to leave a negative. So now you would replug the 1 in. And I don't know what you get and I don't want to finish it. But now you would go replug your 1 into that. And we're going to be done for today. Your homework for today, by the way, is just going to be the wrap up of these notes. I just keep kind of doing a few more examples. It's me doing them in class last year. So you'll hear me, I think, talking to kids you don't know and stuff, but that's okay. I don't want to remake them. And then you need to turn in a Schoology quiz, which I'll put in our week 2 Schoology folder. It might say unit 1. I can't remember how I have Schoology organized because I'm hardly ever in there, but you'll find it. I'll call it quiz for 914. All right, see you later. Have a good one in this meeting.